So in the example on this page, we're given a couple points and are asked to find vector, parametric, and scalar equation of the line passing through these points. So to get a direction vector, a vector parallel to the line, we could find the vector that is between these 2 points. It doesn't really matter in which direction. So I'm going from this point to this point. So that's the tail, sorry, that's the head, that's the tail. So -1 take away -5, same as -1 plus 5. And -2 minus 1 gives us a direction vector of 4, -3. So to write a vector equation, and there's two different possibilities, it doesn't matter whether it starts, since -5, 1 and -1, -2 are both points on the line. It doesn't matter which one it starts with, plus t times our direction vector. So there's a couple different vector equations you can use. In fact, you can also use any other multiple of this vector you want. If you want to use -4, +3, or if I multiply them by 2, 8, -6, that's fine. So there's lots of different vector equations you can write. The parametric equations for the top one, x would equal -5 plus 4t, and y would equal 1 minus 3t. For the second one, it would be x equals -1 plus 4t, and y would equal -2 minus 3t. So there's a couple different parametric equations you can write, one set for each vector equation you write. Now if we take, I'm going to take the top one here and solve for t, because we're asked for the scalar equations as well. So I'll rearrange, I'll bring the 5 over, so it'll be x plus 5 equals 4t, and then divide out the 4, so t is x plus 5 over 4. This one here, I'll rearrange, bring the 1 over, so it's y minus 1 equals -3t, and then divide out the -3. So these are both equal to t, so we equate these. And we cross multiply. So if we do that, 4 times y minus 1 would be 4y minus 4, and that would equal the product of -3 and the x plus 5, which would be -3x minus 15. And we'll rearrange, bring everything over to one side, and so it would be 3x plus 4y, and when I add 15 to -4, I get 11 equals 0. So that is a possible scalar equation. Any multiple that will do as well. Of course, you could multiply everything by 2 and make it 6x plus 8y plus 22 equals 0, and that's still a scalar equation. In the second example, it says find 2 points in the line from the example on the last page other than -5, 1 or -1, -2. The kinds of equations that this is very convenient for are either vector or parametric. I'm going to use the vector. So all you have to do is substitute a number in place of t that doesn't generate -5, 1 or -1, -2. So for example, I'm going to put 2 in place of t. And so this would be 2 times this would be 8, -6. So if we add -5, 1 and 8, -6, we get 3, -5. Of course, that's different than either of these, so 3, -5 would be a point on the line. If we substitute another number, let's say 5 in place of t, 5 times 4, -3 is 20, -15. We add that to -5, 1, and we get x comma y is 15, -14. Now this actually represents a vector which points from the origin to the point -15, -14. So that means that the point -15, 14 is on the line. This is actually a vector, but it's pointing from the origin to that point, so that's why 15, -14 is also a point on the line. So those are 2 other points on this line. In example 3, it says, given these 2 points, we're asked which are on the line x comma y equals 5, 1 plus t times -3, 2. Now, I would find it most convenient to put this vector equation in parametric form. So x would equal 5 minus 3t, and y would equal 1 plus 2t. And what we have to do is find, is there a specific number for t, does one exist, that will generate -7, 9, and then also when we get to the 8, 3, it will generate 8 for x and 3 for y. So what I would do then, if I want to check to see if point A is on the line, I'll substitute -7 in place of x and find what t value gives me an x value of -7. And so I want to solve for t, so I'd subtract 5 from both sides. So we'd have -12 equals -3t. Divide it to -3 and we get 4. So 4 is what generates an x value of -7. So let's see if we put 4 in place of t here. We're going to sub 4 in for t. See if that actually generates a y value of 9. And so it does, because that's 8 plus 1 is 9. So that means that negative 7, 9 is a point on the line. Let's check, see if 8, 3 is. So we're going to put 8 in place of x and solve to find t. So we'll subtract 5 from both sides, so we get 3 equals negative 3t. Divide out the negative 3 and we get negative 1. So if I put negative 1 in place of t here, do I get 3? And you don't, because it would actually be 1 plus negative 2, which is negative 1, does not work out to 3. So that means that the point B, 8, 3, is not on the line, because there is no specific 1 value for t that generates that x and y coordinate. We're asked to now find the vector equation of the line through the point, and we're going to get three-dimensional space here. Through the point, so A is the point negative 3, 2, 1, and is in the same direction as the direction vector 2, 7, negative 1. So here's the direction vector 2, 7, negative 1. 2 this way, 7 this way, 1 down, so there's the vector 2, 7, negative 1. So we're going to draw a vector from the origin out to the point A, negative 3, 2, 1. And this side represents a multiple of the direction vector, so it's some scalar multiple of 2, 7, negative 1. And then we'll join the origin out to this point. So this is actually very similar to that diagram from the beginning of the two-space note earlier in this lesson. So notice in this diagram that O out to P is the sum of OA plus AP. So OP, the big green vector, is the sum of OA plus AP. And we can substitute in place, I'm going to call OP the vector P, I'm going to call OA the vector A, and again, the AP vector is some multiple of the direction vector, so we'll call that TM. So a vector equation in 3-space would look like this. Since the green vector OP is the vector that goes from 0, 0, 0 to x, y, z, we could call it the vector x, y, z. A is the vector that goes from the origin to the point, negative 3, 2, 1, so we could call it the vector negative 3, 2, 1, plus t times our direction vector, the 2, 7, negative 1 vector. So that gives us a direction for our line. If we solve to find the parametric equations, x would equal negative 3 plus 2t, y would equal 2 plus 7t, and z would equal 1 minus t. So those are the parametric equations. And just like in 2-space, remember the constants at the beginning are the coordinates of a point on the line, and the coefficients of t, 2, 7, negative 1, are those coefficients are the components of the direction vector parallel to the line. A little bit of a summary on this page. It says for each of the following, the line contains the point A1, A2, A3 with direction vector M1, M2, M3, and t can be any real number, often called a parameter. Vector equation looks like this, x, y, z equals, this is the position vector of a specific point on the line, plus t times the direction vector, which gives the line its direction. We convert the vector equation into parametric equation. It looks like this. Again, these constants are the coordinates of a point on the line. The coefficients of t are the components of a direction vector for the line. In the last example, it says, given the following parametric equations, find a vector equation for this line. So we're converting from parametric form to vector form. And so notice that 5, 4, negative 6 would be a point on this line, and the direction vector would be 3. Now there's no t here, so the y coordinate would be 0, and the negative 2 would be the z coordinate of that point, or component. So the direction vector would be 3, 0, negative 2. Remember, when it's a vector, the 3, 0, negative 2 are called components. When it's a point, they're called coordinates. It's a very easy confusion to make. So in order to write the vector equation, it would be x, y, z equals 5, 4, negative 6, which is the position vector of a specific point on the line, plus t times our direction vector. So that's a possible vector equation for that line.